right, so ladies and gentlemen, we ended last class doing some dimensional analysis, conversions, things like that, and we're going to get some more practice with that today. But I just want you to be aware that, not all conversions require dimensional analysis, and temperature is an example, okay? Just to refresh your memory, because you learned this in Chem 1. Many times, if we're doing a word problem, your temperatures most of the time will be given to you in Celsius, but very, very often we're going to be needing to be in Kelvin, okay? You don't have to do dimensional analysis, you just have to add 273, okay? There are times when you don't have to be in Kelvin, but most of the time you will, okay? All right, let's talk density. Hopefully from Chem 1 you remember this formula, okay? Mass divided by volume, okay? These are the most common units for density, okay? Grams per cubic centimeter, grams per milliliter. But technically speaking, density can be expressed in any unit of mass per any unit of volume. All right, it's just these are the most common. And for whatever reason, well, actually, let me back up. Let me make sure that you guys remember that the volume expressed in a cubic centimeter is the same thing as the volume in a milliliter. Okay, they are equal in volume. And for whatever reason, solids, all right, if you're given a density of a solid, that is most often going to be expressed in grams per cubic centimeter. If it's a liquid or a gas, those are typically expressed in grams per milliliter. Don't ask me why, it's just sort of one of these little oddities of science. Okay? And if any of you go into the medical field of any kind, or nursing, whatever, sometimes you'll hear a doctor say, I need 20 cc's of penicillin. Well, cc stands for cubic centimeter. So all they're really saying is they need 20 milliliters. Okay. Let's talk a little vocabulary. Okay. These are two words that you see a lot when you're talking about density. Okay, let's actually we'll go in order. Okay, intrinsic, good SAT word. Does anybody know what that means? Intrinsic. Okay, I'll give you a good synonym. Unique is a good synonym. Okay, intrinsic means unique to that substance. All right, if I give you a substance and we figure out it has a density of 20.1 grams per cubic centimeter, it just means there is no substance that's going to have that same exact density. An intrinsic property allows you to identify that substance based on that property. This, however, is a word that you should be familiar with because you definitely learned it in Chem 1. Okay, intensive. Okay, does anybody remember? It would have been from the very beginning of Chem 1. Okay, she's got it. Intensive means a property that doesn't change no matter how much you have. Okay, it's independent of amount. So, for example, you have an ice cube versus an iceberg, okay? The same exact substance, all right? Density being an intensive property, ice cube and iceberg have the same density, okay? What's the opposite of intensive? Extensive, okay? So that means a property that does change depending on how much you have. So think about it. Ice cube versus iceberg. Give me some properties that are definitely going to be different. There's more than one. Volume, mass, weight, All right, those are extensive properties. Okay. So let's look at a practice problem. All right, and guys, anytime we do a word problem in here, I'm going to try my best to model for you the thought process of how to break down these word problems. Because this one is not too long, but just trust me, as we go on through the year, these word problems are going to get more and more complex, and you're given a lot of information, so I'm going to try to model for you how to break them down. Okay, so let's read it. It says, a 55-gallon drum. Okay, drum just means like barrel, container, whatever. But I'm going to stop there. 55 gallons. Gallon, that's a unit of that expresses what? Volume, okay? So I'm just going to put a little V there for volume, just so I remember that. Okay, the drum weighs 75 pounds when it's empty. That's important. What will the total mass be? Total in bold, okay? But look here also, total mass. What unit should my final answer be in? What is mass expressed in? Grams. Okay. What will the total mass be when it's filled with ethanol? Okay. I've given you some information here that is probably going to be helpful. I want you to figure this out. Now, like many AP questions, if you read it once, you may not immediately know how to solve it. Read it again. If you get stuck, talk to people around you. See what you can do. Try this. Guys, as I said last class, if you went about something a slightly different way, that's okay. All right, if you did some calculations in a different order, no big deal. As long as we end up in the same place, I'm happy. So let me say something about, this problem and really any problem in general. Okay, AP word problems are going to have multiple steps. Okay, before you get to your final answer, you're going to have more than one calculation. Let's talk a little bit about rounding. Okay, you can see that at that step and this step and this step, I have done some rounding. I mean, I can't just keep writing decimals all over the place. Okay, but I haven't rounded, very much. Ideally, guys, you don't want to round until your final answer. Okay? So leave these intermediate steps with as many numbers as you can stand, and then round to the end. Okay? Now my final answer here has how many sig figs? 3. And it should. Okay? Now remember, where do you look? You go back to the original problem and look at numbers that are actually printed in that problem. We're not looking at conversion factors, just the numbers in the problem. They had 3, I need 3. Somebody yesterday asked, can I put my answer in scientific notation? Sure. Do you have to? No, I didn't. Okay, but you can. As long as it has the right number of significant figures, I'm happy. All right, so let's wrap this chapter up. Okay, so the end of chapter 1 just talks about matter being defined as anything occupying space, anything that has volume and mass, including gases. Gases, of course, have mass. Okay. We've got solid, liquid, gas. Okay, the thing that differentiates them is what kind of volumes do they have, what kind of shapes do they take. Gases having no fixed volume, sometimes that's a little confusing for people, but a good way to think about it is I could take all of the gas in this room and compress it down to a much smaller volume, and it would still be in the gas phase. Okay, gas particles have great distances between each other, so they are very compressible. Whereas solids and liquids, not so much. Okay. Mixtures, there's two types, homogeneous and heterogeneous. Okay. I'm not going to use this term homogeneous mixture very often. It takes too long to say. All right. This is a synonym. If you ever see the word solution, that means homogeneous mixture. Something evenly mixed throughout. Uniform composition. And just a little tip. If you're ever doing a problem and you see the words something is dissolved in something else. If you see the word dissolve, that's automatically telling you that's a solution. Okay. Heterogeneous is your opposite. It is not evenly mixed, not uniform throughout. Okay. So let's think of some examples from everyday life. How about air? Okay. Tell me some gases that are in the air that we're breathing right now. More than one. Adrian, go. Nitrogen, which actually is the number one gas you're breathing. A lot of people think it's oxygen. It's not. Okay. Nitrogen, oxygen, what else? Carbon dioxide. Okay, those are the three big ones. So let's think about if I took a sample of air from this room and then we went out on 66 and took an air sample on the side of the road, do you think the samples of gas would have the same composition? No, they wouldn't. Okay? And that's how you can answer the question, is it homogeneous or heterogeneous? If you took samples of the same substance from different places, would they have the same composition? And let's use a little critical thinking here. If I took a sample of gas or a sample of air from out on 66, what gas do you think there's going to be a lot more of? Carbon dioxide. Yeah, we're by a major highway. Okay, so air is definitely heterogeneous. How about blood? You know, if I took a sample of your blood, equal volumes, but I took one sample from your finger and I took one sample from your foot. What are some things in blood? Come on, biology. Okay, water. What else? Okay, iron. Not just elements and compounds. Let's think a little bigger. Plasma. What else? What kind of cells? Red blood cells, white blood cells, platelets. Okay. Do you think these two samples are going to have the same composition exactly? No. So blood is heterogeneous. Okay. But anything, as I said, where something is dissolved in something else, that's going to be homogeneous. And we'll see that a lot throughout the year. Okay. Mixtures, guys, are a physical combination, which means they can be separated, okay, by physical means. Okay. I'm going to sort of go out of order here. Okay, this bottom one here, this is a very fancy term for something very simple. If I gave you a sample of ocean water and I said to you, can you give me the crystalline salt back? How are you going to do that? Boil it or evaporate the water. And what will you be left with? You'll be left with a crystalline salt. Okay? So that just means boiling off the solvent. Okay? Filtration is probably your simplest one. You know, if you took a big bucket and scooped out a sample from, let's say, Difficult Run, you know, or any creek or anything like that, think about what's going to be in that bucket. Water, sand, silt, dirt, rocks, sticks, small animals perhaps. You know, you never know. If you ran all that through a filter, what's going to run through? The water, and pretty much only the water. Maybe some of the silt particles. What property is filtration based on? What decides what goes through and what doesn't? What I was really going for is particle size, okay? But your particle sizes in a liquid are going to be smaller than, say, particles in dirt and sand and things like that. Distillation, I'm going to do a demo for you at the end of class. So I don't want to give too much away on this one. I will tell you, though, this is a process used to separate two or more liquids from each other. Okay, but we'll look at this demo at the end of class. And then chromatography is a sort of more specific separation technique. It's used to separate inks and dyes and things like that. I'm not sure if our Chem 1 teachers do this as a lab anymore, but if you have any kind of black marker, like a Sharpie or a Crayola marker that's black, if you ran a black marker on some chromatography paper, you would see that black ink isn't really just black ink. It's got red ink, yellow ink, blue ink, green ink, okay? And you can separate the inks out. And chromatography, again, is based on particle size, okay? It's just kind of more for something very specific. All right, so if it's not a mixture, it must be a pure substance. It's either an element or a compound. Mixtures are a physical combination. Compounds are a chemical combination of elements. Oh, whoops. Well, if you want to separate a compound, you have to use chemical means to do that. You can't separate it by physical means. And guys, that is the end of chapter 1. All right, let me say something about chapter 2. Okay? The big important topic in chapter 2 is going to be really two things: being able to name compounds and being able to write their formulas. Having said that, there is other material in chapter 2, but you guys will notice that the beginning part of this chapter, I'm going to move pretty fast, okay? And as you guys come to get to know how I teach, if I go through something really quickly, it's not that it's not important, it just means it's less important, okay? So I am going to blow through this first part of the chapter to get to the part that is more important, okay? So the first part of this chapter does a lot of historical stuff, okay? All right, talks about Lavoisier being kind of the first research chemist, okay? A lot of, quote, scientists before that didn't really do experiments. They just sort of sat around thinking and came up with these theories, okay? But the big one for him is the conservation of mass. If you mass reactants before and products after a chemical reaction, they will have the same mass. You can't create or destroy mass. Okay? Lavoisier also came up with the law of definite proportions. And when I explain this to you, it's going to seem completely common sense to you. And you'll say, well, of course, duh, all right? But in the 1700s, this was kind of revolutionary. Here's what it says. If I took a sample of water here in Oakton, and then I took a sample of water from Siberia, they would have the same composition. Water is water is water is water. Water, no matter where it comes from, is always 2 hydrogens to 1 oxygen. Okay? And I know that seems really common sense to us, but that wasn't common sense back then. There's another law. Now, listen, don't write this down, okay? This definition is kind of confusing. Let me break it down for you, okay? The law of multiple proportions says this. You can have compounds made up of the same elements, but in different ratios. And ladies and gentlemen, if you change the ratio, you change the compound dramatically. Okay? This is water, obviously. What's the more common everyday name for this guy? Do you know?
Hydrogen peroxide?
Hydrogen peroxide. You got it. Okay? Quite different. All right? You change the ratio. This is very good for us to drink. This will kill you if you drink it. Okay? So you change the ratio, you change it, you change everything about it. Okay? This is just another example. This is laughing gas, by the way. Okay? And this one, I'm not sure this has any kind of everyday use. I know that this is a substrate in a lot of biological functions, a lot of biological cellular reactions. Okay? We're into the 1800s now. We've got Dalton. Don't even write this down. Don't even bother. Okay? The point is, he's kind of the first guy to say the word atom, to realize that there is this small, at that time, thinking indivisible particle that makes up everything. Okay? Getting a little later, we come across Avogadro. And we've got a lot of information here in this graphic, but let me ask you this question. See if you remember from Chem 1. 1 mole of any gas, it doesn't matter what gas it is, 1 mole of any gas has what volume? Remember the number. 22.4. It's written right up there. However, 1 mole isn't written up here. Okay? If any of you were going to answer the question by saying 6.02 times 10 to the 23rd, that's just the number of particles in a mole. What I really want to call your attention to here is that they all have the same volume, they all have the same number of particles, they all have the same number of moles, but you can see they have quite different masses. Okay. Moving on in history, we get J.J. Thomson, who's credited with discovering the electron. Okay? He used this apparatus, a cathode ray tube. He fires a beam of electricity, of light, through the tube. And if you remember, from when you were a kid, you're playing with magnets. Magnets have poles. They have a positive end, they have a negative end. And he noticed that when he held the positive end of the magnet to this tube, that beam was attracted to it. Okay? And if it's attracted to the positive end of a magnet, what does that mean about the beam itself? It must be negative, yeah. And that's exactly what it is. It's just a beam of negative electrons. And in case you don't know, that's all electricity is just a flowing stream of electrons. Okay. All right. Next, we get Rutherford. And you've probably learned about this experiment more than once. Okay. Very famous. What's the name? Yeah, the gold foil experiment. Okay. Okay, he shot a beam of alpha particles. For the moment, what's important about that is that alpha particles are positively charged. Fires it at a sheet of gold foil, and we see 2 observations, which gives us 2 conclusions. Number 1, he notices that most of the alpha particles just passed straight through. What is the conclusion that we get from that? Atoms, what? Yeah, are made up of mostly empty space. Which means what about the size of the nucleus? It's extremely small. Okay? I looked up an analogy for this. and it said if the size of an entire atom is the size of Earth, the size of the nucleus would be about the size of a football stadium. Okay? Pretty small. All right, so the second observation that we get is that a small fraction of these alpha particles did not pass straight through. They bounced straight back. What are they hitting? Okay, the nucleus. What in the nucleus specifically? Protons. Remember, these alpha particles are positive. Protons are positive. Like charges repel. Okay, so we get two conclusions out of this. That there is a nucleus and it's extremely small, and that it contains some kind of positive particle, protons. Okay, this is today's version of the atom. Okay, it's usually referred to as the electron cloud model. You do not need to know these dimensions. Okay. We'll talk later in the year about why it's exactly called a cloud model. Okay. Do not memorize these numbers. Okay. You know their charges. The only reason I put these numbers up here is to illustrate two things. Number one, protons and neutrons have the same mass. And electrons are smaller. Now, this may not look like a big difference to you, but let me put this in other terms. Electrons are 10,000 times smaller than a proton or a neutron. Okay? That's a big deal. That's 4 orders of magnitude smaller. So, electrons are extremely, extremely small. All right. Let's talk a little notation. You're going to see this kind of notation a lot. Let's talk about these numbers. It says the bottom number is the atomic number, which is number of what, ladies and gentlemen? Protons. Mass number is the number of what? Protons plus neutrons. Let's do a little mental math. How many neutrons does this guy have? 20. 20. This is protons. That minus that is 20, okay? If your number of protons, which is your atomic number, is equal to electrons, you have a neutral particle. What if they're not equal? It's not a neutral particle anymore. What do you call it? It's an ion, okay? So, potassium, for example, carries a +1 charge. Anything that has a positive charge means what happened? Yeah, it lost electrons. And specifically, this one, how many did it lose? Just 1. It had 19, now it only has 18. All right, what if I do that? What does a negative charge mean? Yeah, it gained electrons. How many did it gain? It gained 2. So this particle would have 21 electrons. Now, this is an ion that doesn't exist, but it's just for, explanation purposes. Okay. So we're going to be looking at covalent compounds. We're going to be looking at ionic compounds and acidic compounds as well. Right? Remember that your covalent compounds are between 2 or more nonmetals. And if you have a covalent compound, you are permitted to use this word molecule. Okay? Now, there's a little pet peeve of mine here, okay? And somebody should really write this down because over the course of the year, I'm going to have like 1,000 pet peeves. This is a word you can only use if you're talking about a covalent compound. If something's not covalent, what's the other type of compound? ionic, okay? You can't use the word molecule with an ionic compound. Does anybody know what word you can use? So it's like an analogy. Covalent is to molecule. Ionic is to blank. Do you know the word? Salt, yeah. Okay, not meaning table salt, although that is an example of an ionic compound. Okay, but that's a word you are permitted to use with an ionic compound. Okay, blah, 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 blah. Okay, we're going to be dealing with chemical formulas a little bit later in the year. When we get into winter, we'll start drawing structural formulas. We're not doing that today, though. Okay, just a little vocabulary review. Positive ions called cations. Some people say cation. I don't know, I think that's kind of weird, but hey, you know what? You do you, all right? You do what makes sense to you. Negative ions, anion. Okay? And please don't shoot the messenger. But when you're talking ionic compounds, we've got to talk about polyatomics. Okay? And I have made, much like you probably had in Chem 1, I've got a sheet of polyatomic ions for you. Now, in Chem 1, you likely had to memorize some of these. Okay? Here's the deal. Okay? College Board is going to expect you to know all of these. However, I'm going to tell you which ones are probably more common, okay? The ones that you absolutely must know, okay? So if you want to highlight or put little dots next to it, okay? These are also likely the ones, if you did memorize in Chem 1, they're a lot of the same ones. So here we go. In the first column, I would definitely know acetate, hypochlorite, chlorite, chlorate, perchlorate, bicarbonate, nitrite, nitrate, and hydroxide. Middle column, carbonate, chromate, dichromate, sulfite and sulfate. Third column, phosphite, phosphate, and ammonium. Okay, if you know those, you're good to go. Now, could a test or, the AP exam ever throw like cyanide in something? Well, yes, but that's really not very likely. Okay, so focus on those, and if you have time to learn the others, great. But keep this out. You'll need it later. All right, let me say something about the periodic table that I gave you last class. Okay, that periodic table is yours, your personal property. You are more than welcome to write all over it, label it, maybe with the family names, color code it, whatever you want to do. Draw kittens on it for all I care. Okay, whatever. It's yours. When we take tests in here, you will use one that looks exactly like yours, except it won't have anything written on it. Okay? So, while we're on that topic, some people, especially at the beginning of the year, like to use their periodic table from Chem 1. That's fine. However, I would kind of caution you against doing that just because your Chem 1 periodic table has a lot more information on it than ours does. And I don't want you to get used to having that information. Okay, so just something to think about. Okay, in general, this is where your metals are located. All right, that includes everything down here in your lanthanide and actinide series. I want to call attention to one particular box. This guy right here. What element? Hydrogen. Okay? True or false? Hydrogen is in group 1. True or false? It's not a trick question. True. Is hydrogen an alkali metal? No should be the resounding answer. Okay? Hydrogen is definitely not a metal. Okay? It's a non-metal. That is not highlighted yellow for a reason. Okay? Properties in general, metals, excellent conductors. They tend to lose electrons. And by the way, just a little factoid to share over the dinner table. That is the most misspelled word in the English language. Because you know how most people, like more than 50% of the population would spell that? L-O-O-S-E. Okay? Don't be one of those people. All right, but if something loses electrons, what kind of ion does it form? A cation. Remember, electrons are negative. Okay? Metals are very malleable. What does that mean? Yeah, bendable. Okay? They're very ductile. What does that mean? Okay, they can be stretched out into wires. Do you know what's the most ductile metal on Earth? It's not what you think. What's the metal that's in basically all of our wiring? Copper. Copper is a very ductile metal. However, it's not the most ductile metal. It's a very expensive metal. It's gold. Okay? Gold is the most ductile. The only reason we don't use that in most of our electrical wiring is it's too expensive. Okay? There's where your nonmetals are located. Okay? In solid form, they're very brittle. You drop it on the floor, it's going to shatter into a million pieces. Nonmetals tend to gain electrons, which means they form what kind of ions, ladies and gentlemen? Anions. Good. Okay? They form covalent bonds. Metalloids. I actually want to call your attention to the periodic table on our wall here. Okay? You will see on our periodic table there is an orange staircase marked out. Any element sitting on or below the staircase is considered a metalloid with one exception. What element? Aluminum. Ladies and gentlemen, aluminum is definitely a metal. Think about aluminum foil. Okay? And as for properties, we're just going to say that metalloids are metal-ish. Okay? That's as far as we're going to go with that. All right, let's get to the good stuff here. I've talked really fast. This is where I want to focus. Okay? Naming compounds. Let's start with ionic. All right, you did this in Chem 1, so this should be pretty quick. All right, remember, you don't change the name of the metal. You only change the ending of the non-metal. And the one and only nice thing about polyatomics is that no matter how it is, if it's a cation or an anion, you don't change the name. Okay? It always stays exactly as it's printed on here. Okay? There's basically two types of ionic compounds. This is one. The other, if you remember back from Chem 1, some things have a Roman numeral in their name. And the reason that is if you come across a metal that can carry more than one charge, where are those elements that can carry more than one charge? Okay, transition metals, and some of the metals underneath that staircase, like lead, for example. All right? So when you're naming an ionic compound, you need to ask yourself, does this metal need a Roman numeral or not? For example, anything in group 1 has what kind of charge? Always. +1. Things in group 1 don't need a Roman numeral. Anything in group 2 has a charge of +2. Okay? Transition metals gets a little murky. okay? But what about boron's group? What kind of charge? +3. Carbons, the carbon family, those are elements that kind of can go either way. They can be cations or anions. How about nitrogen's group? Charge. -3. Oxygen's group? -2. The halogens? -1. Okay? So if you come across an element that does need a Roman numeral, you don't have the charges on here. So you've got to figure it out. All right? So we're going to look to the nonmetal. Can you guys tell me, chlorine carries what charge? Okay, -1. Oops. Times 2 is -2. So to balance that out, this lead must be +2. Okay, and it is. All right, so we would call this lead Roman numeral 2 chloride. But let's look at some other examples. How about this? First of all, what element is Cr? Chromium. Look at where chromium is on your periodic table. Does it need a Roman numeral, yes or no? Yes, it does. Okay. Well, we don't know what its charge is. Let's look to the nonmetal. Oxygen in this case is going to have a charge of -2 times 3. So that's a total negative charge of -6. +6 is going to balance that out. But don't write chromium 6 oxide. There's 2 of them. So each one must have a charge of what? +3. So this would be chromium Roman numeral 3 oxide. Now I need you to be careful about something. Because if any of you were thinking, oh, well, of course that's +3, you can just, reverse these numbers here. Be careful, that doesn't always work. Like, what if I had that? What element is that, first of all? The metal. Iron. Does iron need a Roman numeral? Yes? Okay. If you were, kind of getting lazy and thinking, oh, I'll just switch the numbers here, well, this has a subscript of 1 and 1. This is not iron 1 oxide. What's the charge of oxygen again? -2. So this must be +2. Iron 2 oxide. Okay. Your covalents are much, much easier. 2 or more nonmetals, guys, to refresh your memory, this is where you use those prefixes. Whatever the subscript is, that's the prefix it gets. Mono, di, tri, tetra, pent. What's the prefix for 6? Hex, 7. Hept with an H, 8. Oct, 9. Non, 10. Dec. Okay, we're not going to go beyond that, dodeca and all that now. All right. So, quick example. Again, it's just based on the subscript. Diphosphorus. Don't change the ending. You only change the ending of the second element. Pentoxide. Let's see what you remember. And I'm just making this up. This is probably a compound that doesn't even exist. If I had that. What's the name? Nitrogen trifluoride. How come you didn't say mononitrogen? Got it. Okay. That's the only little hiccup to this set of rules, the only little exception. The The prefix for mono only goes with the second element. Okay? All the other prefixes you are permitted to use. So, here's what I want you to do. All right? We'll probably only get to this slide, although if you finish it, go on to the next one. But I want you to name these compounds. Might I suggest that before you just launch into naming them, decide for yourself first, is it ionic or is it covalent? Which system do I need to use? Okay, try it.